Hey guys, in this tutorial we're going to take a look at how to create something like this spanner just using simple geometric proofs. Alright, so we're going to dive into Photoshop just so that I can explain some of the base work for this. It's not very complicated. Basically we have this hexagon and we have a number of sides to that, which is 6. And then we have this capital R, which is uh, the radius from the center to one of the points of the hexagon. We also have this little r, which is called the inscribed radius, which is the distance from the center to the midpoint of one of these sides. Now we also have this L over 2, which is our side length divided by 2 because we're only concerned with this portion of it for now. And we also have theta, which is a sub-angle of the interior of this hexagon. Alright, so oops. Okay. So the first thing we're going to look at is our theta. So our theta is equal to 2 times pi divided by our number of sides divided by 2. And the reason for that is because we're missing this section of the triangle. So there would be 6 larger triangles, but we're only taking half of that triangle. That's why we divide it by 2. So that becomes 2 pi over 2n, and the 2's cancel out, so our theta is equal to pi over n. Now beyond that, let's say, okay, now we want to calculate, we're going to use L for our base sort of measurement for everything. So in order to calculate R, we're going to take the sine theta, we're going to say sine theta is equal to 0.5 L over R, because R is our hypotenuse and L over 2 is our opposite angle to theta. So from that we can say R equals L over 2 sine of pi over n. And similarly we can do the exact same for our little r. So in order to calculate that we use tan because we have L over 2 which is our opposite and little r which is our adjacent. So we say tan of theta equals 0.5 L over little r, and so little r equals L over 2 times tan of pi over n. Alright, so those are the 3 equations we're going to use in order to create this definition. Alright, so let's jump back into Grasshopper. I'm going to get rid of this, and I'm going to create a new document. So I'm going to start out with a line. I've already prepared one earlier, but it doesn't matter what line, just put a line in, and we're going to reference that in as a curve. I'm going to set one curve, and then I can hide it again. And I'm going to use my curve frames tool, and all I want is one division along this. So I'm getting 2 frames, one at the beginning and one at the end. And now I also want these frames to be facing the same direction. So what I'm going to do is I'm just going to create sort of rotation angle in here, and so I'm going to rotate these planes by this angle, and we'll see if that's done it the right way. Maybe, we'll find out in a sec. And now I'm going to create a polygon. And so this polygon, you can see, okay, here is our radius of polygon. This is going to be capital R. So we're going to bring in our first expression. If we go back and look over here, R is equal to L over 2 sine of pi over n. So we'll type that in. L over 2 times sine of pi over n. We'll close our parentheses off, and we'll just relabel some of these. So L and n. And then I'll drop down a slider, and I'll give it a maximum value of 10. And I'm also going to drop down another integer slider this time, and this is going to have a maximum value of 12. And I'm also going to connect it up to my s, which is my number of sides, not called n for the component. And then I'm going to plug my radius in here, and we're just going to recompute the solution. And there we go. So now we're getting shape. We just need to put it on our plane, and let's see, it looks like it's facing the wrong direction, so I'm just going to flip this around, and I'm going to change it to pi and 0. And so there we go. Nope, we're almost there. The other thing, okay, I might also need to bring in another expression, another one that we created, which was pi over n, and we're going to add our angle, which we'll just call x. So this is going to be our x, this is going to be our n, and we'll plug that into our angle, and there we go. So now our planes should be facing the right direction for any number of divisions. We're almost there. Maybe it is the other way around, 0 to pi. Yeah, there we go. So I've always got this long edge, or these long edges facing each other. Alright, so now we're going to bring in... Alright, let's see. Wait, what do we need to do next? So now we need to just create a surface, or another sort of curve to link these together. And the reason why... Okay, well now we can do this in a purely mathematical form. I'm just going to go to my top view, rather than sort of deconstructing these curves and finding these corresponding endpoints and drawing a line between them. We could grab the length of our curve over here, and then what we're also going to grab now, we're going to copy this expression, and this time we're going to use our little r, which is our inscribed radius. And so the formula for that is pretty much the same, except it's 2 times tan of pi over n, or L over 2 times tan of pi over n. And so what we're going to do is we are going to create another expression, which is going to be this length. Actually, I don't even need to use an expression, I can just use a minus. We're going to minus this length from here. And now we're going to, we're also going to create a third curve frame. What I might do is bump this up to 2. And then we'll dispatch these frames. And so these frames will go in here, and my middle frame will become the base for a plane surface. And so this is the plane, and so let's see which way this goes. Is this my X? Yep. I'm going to, actually I will drop down an expression then, because what I'm going to do is I'm going to go X over 2 minus Y. So this is my X over 2, this is my Y, and we're going to construct domains for each of these, and so I also need a negative value so that I can plug I can go from negative this value to positive, and so you can see that lines up perfectly with the edge of our hexagon. And then I'll just move this along a little bit so it's a bit easier to work with. I can get rid of that. And then I need to do my Y as well, which is going to be this value here, and it's probably going to be X over 2. Well, we'll call it L over 2, just to be consistent, well, semi-consistent. And we'll need to do the same thing, construct a domain, negative to positive. Oh, I did not want to group that. Then plug that into my Y, and there we go. Now we're also going to scale this polygon in, and we're going to scale it about our center, which is our plane over here, and we just need a factor. And then I will just move that plane up in a positive Z direction by a certain slider value here. I'll give that a maximum value of, I don't know, 3. Now we're going to just go into perspective view and see what's going on. In fact, maybe I will, maybe I'll slide, no, we can leave that for now. So now what I'm going to do is I'm going to loft between these 3 things that we've created here. So I'm just going to graft this output, and I'll check that my data structure is the same all the way through. Yes, it is. So I can now loft between 1, 2, oh, not quite. What's going on there? Yes, I also need to graft my planes. And then 3. And I'm going to change this loft option to straight sections and commit changes. And then I'm just going to, actually, you know what, I don't need to do this last bit just yet. I'll show you another workaround for that. So we've lofted that. Now we're going to deconstruct that B-wrap, and we are going to use a mesh surface component. And so I'm going to mesh each of these faces. I'll give them a maximum value of 5. So let's see. Alright, and I'm going to do the same thing, mesh surface here. And we want one of these to match up. Not sure which one at the moment, but it looks like the right one matches up. So that's good for us. Let me just turn everything off. Cool, so now if we change this, our divisions on the plane and on this hexagon update automatically. I am going to put in a different slider in my U value over here though, because I might want more divisions along this axis. Alright, so now we can, now that these are meshes, we can use Weaverbird join to join them up. We will flatten them, and we may have an issue with normals here. I'm just going to weld my vertices so that we can check what's going on. Yes, it looks like there is an issue. Yeah, you can see as soon as I bake that out, we do get this black row of faces over here. So what I'm going to do is I'm going to mesh flip this set of faces, and then disconnect this here and reconnect that there. Plug that in. Oh, I shouldn't have gotten rid of my weld vertices, but this time when I plug it in and bake it, we should have no issues. Good, there we go. Right, so now what we can do, actually, you know what, I feel like I do want another extrusion, or like another layer to this this inner ring here. So I'm going to move this along, and I'm going to scale this geometry one more time, and then I'm also going to move it based on a multiplier of this vector here. Alright, so now I'm going to preview this off, and I'm going to add that into my loft. There we go. So now I can mirror this geometry, and I can mirror it through an XY plane, I believe, at the location of this Z vector here. And so there we go. I might bring that down a little, but then I can also bring this sort of inner division back up a little. And I also want a separate slider for my scale factor for the second part of the wrench here. And I'll bring that in a little bit, make that one a bit smaller, and there we go. So now I just need to connect these up. And the way I'm going to do that is I am going to use a component from Weaverbird which is called the naked boundary. And so this will give me the boundary of these, all of the naked faces, the naked edges, sorry, so that I can loft these together. And so I'm going to graph this, and I'm going to throw down a loft component. I'll loft that one and that one, and there we go. We've got a close, oh, we've almost got a closed piece of geometry. I just need to deconstruct this B-rep. And in fact, if I do mesh UV it, actually, that seems to be working quite well. Let me see what happens if I change these divisions. Yep, looks like it's all going to correspond. And like I did before, actually I will add a separate subdivision. I think it's for my U. Yes, so that I can add some more sort of edge loops along that edge as well. And then I'm going to use my WB join again. Actually, yes. And so we're going to join this set of meshes up with this one and this mirrored one as well. and then we're going to flatten the output, the input, and we're going to weld vertices again, and just see if we've got any more issues with mismatching normals, which there is a good chance at this stage. Yeah, so I can't quite tell. I'm going to do a Catmull-Clark subdivision. That'll give me a bit more of, that'll give me a bit better understanding of what's going on. Yes, so it looks like we do have an issue coming from this here. So I'm going to mesh flip this here. Mesh flip. And then I'm going to disconnect that and plug that in. Whoops. And then we'll see what happens with our Catmull-Clark. And you know what? That is looking better. Except, yes, and now we've also got an issue on the bottom. And so all we need to do is just flip the bottom around as well. We're going to flip that. Wait, we'll flip it here. Disconnect it from this join, and then connect it back into there. Get rid of this. See what happens when we bake this. And that is looking much better. I'll increase my subdivisions just to check that everything is working properly. Oh, no. Not quite. Alright, so now we've got to figure out what's going on here. I have a feeling... yes, okay. I see what the problem is. We've got this sort of mismatch of faces along this edge that I probably should have realized would happen. What I am going to do is I'm going to explode the curves over here. And then I'm going to explode these ones as well. And then I'm going to graft those and reconnect those into my loft. And then I'm probably going to disconnect this slider here. Actually, no, I don't want to disconnect it. I'll want to give it a subdivision of 1. So there we go, that should now be matching up properly. Preview all of this off. And hopefully, there we go. Nice, clean spanner. And so now, we can go back to the beginning, and we could, let's see, where is it? I could give this more more edges along the spanner. I can control the length, and this is really good because by reducing the problem or the solution to a purely mathematical reasoning, it means that you don't have to struggle with trying to make sure you're always going to get the right vertices over here to connect up, because you can imagine as soon as I increase this number, there's the chance that my vertices are going to completely misalign. But this is, like I said, this is a really great way to do it. And then maybe I want to tighten this edge up a little bit, so I'll keep that scale at 1, and I might also want to add another subdivision along here, because that's kind of bugging me at the moment. And there we go, now I can bake this out again, and there's my parametric spanner. Cool. Hope you enjoyed it.